did last time was to tell you a lot about SU2 and SO3, which is it's actually a quite confusing subject. So I mean, if you can kind of anyway, it's extremely confusing. I think the underlying story, you know, once you get a handle on it and start to see what's going on, it's not that bad. There is a straightforward story there, but it takes a while to kind of understand what that is. So one thing, what I wanted to do is maybe start by asking if there are any questions about that, and then also I want to spend some time at the beginning of the class going over what we did last time, so to kind of summarize that and to say more about what that, you know, what the kind of bottom line you should keep in mind is about that aspect of the subject, and then what we'll do is then go on into the rest of the class. I'll talk about the spinor representation and about some more kind of the physics applications of this. I'll start to say a little bit about how to connect the all this mathematics we've been doing with SU2 and SO3 to physics. So, but maybe to start, are there any questions from last time? Do you guys have anything?
Yes, I just have a question about the concept.
Yeah.
When you speak of the isomorphism between Lie algebras, what exactly do you mean?
Okay. Oh, I guess I should just say that yes. So an isomorphism of, I'm not sure. I guess an isomorphism of Lie algebras is, well, maybe it's better. Let me just first just say it. An isomorphism, whenever you've got any kind of algebraic kind of structure we're talking about, and an isomorphism of the algebraic structures is something that is a one-to-one map on the sets, and then and then it preserves whatever the algebraic operations are. So for a group, you say that two groups are isomorphic if there's a one-to-one map, if there's a map between the two sets, which is a homomorphism, which respects the group multiplication. For a Lie algebra, a Lie algebra isomorphism is just going to be, so remember, so a Lie algebra is basically, the only data there is a vector space and then this bracket operation. And so if you want to say the two Lie algebras are isomorphic, you have to just find an isomorphism of the vector space. It's just a linear map from one vector space underlying the first Lie algebra to the vector space underlying the second Lie algebra. That's an isomorphism. And that's just a linear map that's a one-to-one linear map. But then you have to show that that preserves the brackets so that the map, if you take the map and apply it to the bracket of two things, you get the bracket of the maps applied to the two things themselves. Okay, does that help?
Yeah, definitely.
Okay, so that's the general. Any other questions about last time? Because I will spend some time going over it, because I think this actually is really hard to get a handle on the first time you see it. Okay, let me then get started on that, and we'll stop for a minute after I do a little bit of that and see if you have any questions, you find anything confusing about this. But so what we were talking about really was last time was really two groups. So there's first I'll tell you the story that I was trying to tell you at the level of groups. Okay, so at the level of groups, this was really about, you really had I defined two groups, one I called SP1, and this was the unit quaternions. So you just take quaternions of unit length, and then if you take the inverse of a quaternion of unit length, it's also a quaternion of unit length. And then the multiplication of the group was just the multiplication of quaternions. Okay, and then what I showed was there's another group, SU2, which looks very different, which is 2 by 2 complex matrices, unitary, and determinant 1. Okay, so these also form a group, and now the group operations is just multiplication of matrices. And again, okay, so now these two things. So then I also showed if you try to show explicitly that these are actually isomorphic, that you can actually, you can associate to any unit quaternion, you can associate one of these. And both of these, sometimes I'll also give them the name. So these are equal, or they're isomorphic. Again, in the same sense, maybe that there's a map from here to here, which is a one-to-one map on these things as a set, which is a group homomorphism. You can see that. And these also are sometimes called, I'll also sometimes refer to both of these as spin 3. Okay, with the idea that there's whenever it turns out in any dimension, when you have a rotation group, there's a double cover of that rotation group, and it's called the spin group, and this is the spin group in dimension 3. So we talked about those matrices, those kind of groups, but then the tricky thing was the relationship to SO3. Okay. And SO3 was the 3x3 orthogonal matrices. Those are real matrices. And again, with determinant equal to 1. And for orthogonal matrices, the determinant is just plus or minus 1. So this determinant condition just picks out one component of all the orthogonal matrices. Okay, and then now the the relationship between these things. So the is what's subtle, and it's given by this map. So there exists a homomorphism by, I'm going to write this down. So it's spin 3 SO3, and that's a double cover. Okay, so what this means is that there's these guys. There's a map that doesn't quite identify these things. It takes everything in here, everything in here to a point in here, and every point in here comes from something here. But the subtlety is that it's a double cover, that to any point in here comes from 2 points in here. Or in other words, if you find a group element here that gets mapped to here, then minus the same thing will also get mapped to there. And I wrote that, and if you want to write this map down really explicitly, it's hard to do using SU2 for spin 3, but if you use the SP1 for spin 3, then there is a conceptually nice way of writing down what this map is. And what it is just what you do is you take, well, the way you write this down is you identify R3 with the imaginary part of H, the imaginary is by taking something with components V1, V2, V3 gets identified with V1I plus V2J plus V3K. So you think of R3 as being the quaternion set whose real part is 0. And then this map here becomes, okay, and then then if you think of spin 3 as SP1, it's a unit quaternion. So if you take U, a unit quaternion, then the way this map works then is that it takes U. So U is a unit quaternion. You want U to a homomorphism that takes U to a rotation in 3 space. Well, the way to see what rotation you're going to get is you look at the rotation that takes a vector where you think of it as a unit, as an imaginary quaternion, and then you just conjugate by this guy. Okay. So this is kind of a conceptually very kind of clean way of describing what's going on, but it's a little bit confusing to wrap your head around and to try to understand well enough to kind of produce nice formulas. But this is the idea, and you can see here that one way to see that this is a double cover is that if you find some u that gives this rotation, then minus u gives it, so minus u is the same rotation as u. Okay, because the minus signs cancel here. Okay. So this is the basic idea. And now to try to make this a little bit more explicit. Okay, but maybe first up here, are there any questions about this whole the basic setup of this? No. Okay, so let me then go on. So then, I mean, what's hard then is to get from this high-level kind of conceptual explanation of what this guy is to get this down to understand how to actually work with this thing and how to work with how to derive formulas that will show you how to do this. So let me kind of say a bit about that. Let me stop with this. So then okay, so here the more you can get this very nice explicit formula this way, and what you find is that you find it, start thinking about what are the simplest rotations. If you want to break down a rotation in three-dimensional space, it's generally you want to think about it as being either a rotation about some axis or maybe a product of rotations about different axes. So you want to know how do I rotate something about an axis? And the way you rotate something about an axis is this way. So rotation by an angle theta about w vector. So you have to pick a direction that you can rotate about, and let's take that a unit vector. It's just given by x vector goes to u x vector u inverse, where u is equal to e to the theta over 2 w vector. What else I want to say? And this you can, if you expand. So now I'm going back and forth here between thinking of these guys as vectors in R3 and thinking of them as purely imaginary quaternions. But here it's just quaternion multiplication, and this is given by cosine theta over 2 plus w vector sine theta over 2. And so this is. And here, just implicitly, there's like an identity quaternion. This is an identity of quaternions. So in terms of quaternions, this whole thing is very, very much like what you're used to in the plane. In the plane, you just had you instead of having some linear combination of I, J, K, you just had I, and you had some formula like this. Now, but the one really funny thing that's happening, because the way you're doing this is by conjugation, is that here half the angle is appearing and here the full angle. So what happens? So the picture of what happens is that if you if you go in a circle, let's say so if this is a circle of rotations, from about some axis, let's say, I want to say this about, anyway, let's say W. Starting at theta is equal to 0 to theta is equal to 2 pi. Okay. So let's say you start here where this is the identity, and then you start moving around. This is theta, so this is theta is equal to 0, if you like. This is theta is equal to pi. And then you come back, and here again it's 2 pi. But you just imagine this is kind of a loop in the group. It starts out at the identity, and then it does a rotation about an axis and comes back to where you start. Now, so these are kind of a loop of elements in SO3, and for each one of these, you could ask, what are the elements of spin 3? What are the unit quaternions that do this? Well, if you pick any one of these things, so you can start out with the unit quaternion 1, and then for each one of these guys, you just pick this guy. You use this formula. And then so here you're going to be up in SP1 or spin 3, and then as you go around from theta is equal to 0 to theta is equal to 2 pi, you go here from theta is equal to, anyway, the theta over 2 just changes from 0 to pi, and e to the pi w vector is -1. So what happens here is you go around, and then you come back, but it doesn't close. You end up at -1 is equal to e to the pi times a, so e to the pi times a unit quaternion is going to, if you check, it's going to give you -1. So you're going around here, and then your problem, so your problem is that you don't have a. And then if you keep going from, so here we're going from 0 from circle. Anyway, this is the same picture. So if we kind of keep going, if we went from 0 to 2 pi and then kept going all the way around twice to 4 pi, then you would go around and you would come back to where you started. But so you have to go around a circle twice down here to go around a circle once up there, and this kind of shows how you get why this is a non-trivial double covering. So each point in here is going to correspond to the point up here with theta over 2, and the point up there with theta over 2 plus pi plus 2 pi. Look, plus pi. So you have to. Anyway, so it's this 2 that causes the double covering. But another way to see it is just to see that if you do a rotation down here, it's not, you don't get a, you get an ambiguity. To theta is equal to 0 here is going to correspond to, or 1 here is going to correspond to 1 and -1 up there, and you don't really know which one it is. But if you go around the circle once here, you go from one to the other. So that's this is the source of subtlety. I mean, people often then you can often talk about this in terms of topology, that this, there's a map, this phi is giving you a map from this space here, which you can think of as being a three-dimensional sphere down to RP3. So this map is going to turn out to be the same topologically. This map is the map from the points on the three-dimensional sphere to the points on the three-dimensional sphere with opposite points identified. But you have to. But the thing you don't see just by looking at the topology, and if you ask the topologists, they'll anyway they'll understand that this is a non-trivial double cover, and interesting thing to study as a bit of topology. But the extra thing to realize here is that phi is actually a homomorphism. Phi is not just a map, not just any kind of, not just a continuous map, but it actually respects the group location. Okay, so that's pretty much all there is to say about the groups. Any other questions about the groups, about SO3 versus? No. Okay, let me get on then to, so then the next tricky thing to understand is about what does this tell us about Lie algebras? Well, the thing is, remember that so Lie algebras, okay, so the thing about the Lie algebra is the Lie algebra is just, is geometrically, it's the tangent space at the identity, but the difference between SO3 and SU2 is you only kind of see globally. If you just look, if you look just in the neighborhood of the identity, you see that it's just that mapping phi is just a one-to-one mapping, and it really just, if you look at its derivative at the identity, it's just the identity map. So the Lie algebra situation is confusing in that the Lie algebras are all isomorphic in the sense that John asked about earlier, that there really are, all of the groups that I've talked about all have exactly the same Lie algebra, or they're isomorphic Lie algebras. And maybe let's just write that down. So the Lie algebras, so here we have that the Lie algebra of SP1 is equal to the Lie algebra of SU2, and it's equal to the Lie algebra of SO3. So that they're all the same thing, but they initially can look different, and they initially, so here you have, so in terms of bases, here you have a basis is just the I, J, and K. So all of these guys as a vector space are just a three-dimensional real vector space. Here you have a natural basis I, J, K. Here you have, and I want to do this take minus I, sigma 1, minus I, sigma 2, minus I, sigma 3. And then you have an isomorphism of the algebras that maps this elements of this basis to this basis, and I'll say, and that preserves the Lie bracket. That's the thing I'll say in a minute. And then for Lie SO3, I called it like L1. I called was the infinitesimal rotation about the first axis. So that's the thing that looked like -1, 1, 0. Okay, and then there's L2 and L3, and these guys. Anyway, this is just the permuting to the other two axes. And now, and again, so here you have a basis for a three-dimensional real vector space, but these are all so these are isomorphic. So identifying these basis elements preserves the bracket. The Lie bracket definition, which is a commutator. So in each of these cases, there's a Lie bracket operation, and it's just the Lie bracket of two elements is what you get by multiplying the two elements in the opposite orders and subtracting. Okay, and you can anyway. So you can check that this works out for these guys. But then there's another isomorphic structure. Or if you just take as basis elements the standard basis vectors on R3, so E vector 1, B vector 2, 3. Okay, so just this basis vectors of R3, and then take it as the bracket. The bracket. I won't try to write this down, but the bracket is the cross product. Okay, so that if you take the Lie bracket of any two of these, it's given by taking the cross product of the two. And anyway, the cross product is also anti-symmetric, just like the commutator. And you can see that this structure is also isomorphic to this structure. Okay, so I think mathematicians like to think about this. If you think about this abstractly, that there's a single abstract object, the Lie algebra. It's R3 with this bracket map on it, and there's many different kind of isomorphic ways of realizing this, of getting it more concretely, and they're given by these four different things. So this looks like this is quaternions, this is three-dimensional vectors, this is skew adjoint 2x2 matrices with trace 0. This is anti-symmetric 3x3 real matrices. They look like very different structures, but they all have the same thing, and it corresponds to the fact that locally these three groups, SP1, SU2, SO3, they all their tangent space near the identity always looks the same, and it looks like this. Okay? So at the level of Lie algebras, you don't see the double cover at all, because it's if you just look at what's happening near the identity, you don't see the identity in the two groups. You don't see this. Okay, and then maybe the last thing to say about this is the other thing to say about the Lie algebra is when you have the Lie algebra, you also have a three-dimensional irreducible representation of the group, of the corresponding group. So these give irreducible Lie group representation, reps, which is add, which is the thing it takes. It takes a vector in R3 to G to add to G Y vector G inverse. Anyway, in any of these, so in any of these, this makes sense in different ways in any of these pictures with any of these groups, and a Lie algebra representation, the algebra rep. So add, which takes Y vector O3 goes to X vector Y vector. So this is what I would call small add of X. Well, anyway, let me just. So this is what I would call small add X. I'm running out of space here. Sorry. Small add of X applied to Y, and this is what I would call big add of G applied to Y. But anyway, so in terms of representation theory, the Lie algebra always gives you a distinguished representation of the group, and it's anyway, so it's a representation on the vector space of the algebra. And the one thing which I'm not saying much about here, the confusing thing about this is that here you've got a real representation, but our general theory of representations wants to deal with complex representations. So you have to, wherever I talked about real linear combinations of things, you should try, talk about complex linear combinations of them, and then you have a complex representation. Okay, so any questions? So this is pretty much the end of the review of yesterday. Anything about last time? Any questions about that? Okay, so let's get on to, so what we're going to do today, the kind of summary of what I'm trying to do today is to tell you about that, once you know about this, once you know about the SU, that this group, that the double cover of SO3 is SU2, you end up with a, you have a new representation to think about, but it's not, but there's nothing at all kind of interesting or tricky about it from this point of view, which is that okay, so and actually maybe before I go on, I should say, well now, so we'll mainly use SU2, not ST1, because we want to study complex representations. So there's two reasons why, now that I've told you that quaternion is the right way to think about what's going on and to do some kinds of calculations. Well, those calculations, it really works well for if you want to do calculations in the group spin 3 or in the group SO3. But if you actually want to talk about the representation theory of the group, having your underlying algebraic objects in the group be quaternions makes the whole situation kind of algebraically complicated because you need to go between quaternions and complex numbers. And so it's bad enough that we have to go from real numbers to complex numbers, but to throw in quaternions into the algebra, if you're going to do representation theory, is tricky. And also physicists are really used to the physics calculations are all in terms of SU2, in terms of complex numbers anyway. Okay, so now if we talk about SU2, well, we saw that SU2 has, we know that it has a trivial representation, linear representation, and then it has this three-dimensional adjoint representation. But there's an even more obvious representation for SU2. So let's just take the obvious other irreducible of SU2 is just the defining on C2. I mean, you're realizing these elements of the group as 2x2 matrices. So 2x2 matrices operate on C2. Complex matrices operate on C2. And so, in other words, so pi of G is just G. That's what I mean by defining representation. And so this is called this is the spinor representation. And we'll also, in a minute, we'll see later, it's also sometimes called the spin 1/2 representation. Okay, and so to get ahead of ourselves, what I'm going to do next on Thursday is tell you about to write down all of the irreducible representations of SU2 or of SO3, and we're going to find that they're labeled by a non-negative integer n, and then you say that the one labeled by n you say is the spin n/2 representation. And so what you've seen, so 0 is going to be the trivial representation, 1 is going to be the adjoint representation, the one that we've seen on vectors, and then this is going to be, n is, well, in that way of counting, n is equal to 2, well, anyway, so this is going to be the one that's called spin half. Let me not try to get ahead of myself. Okay. So from this point of view, if you realize that instead of thinking about SO3, you should think about its double cover, SU2, and you know that its double cover is SU2, then you automatically see that the double cover has an interesting new irreducible representation. And the tricky thing about this is that okay, so here, so the tricky thing to notice is that the spinor representation is not a representation of SO3. Okay, so I'll try to explain why this is true. But the point is that we've got something which we think of it as a replacement or as an enhancement of the rotation group, but it's got a it's kind of defining representation. Its simplest representation is not a representation of the rotation group. And maybe one thing to say is this, is that, so that we have, so since the relationship we have between SU2 and SO3 is a homomorphism. That if pi, let's see, now this is where I always get confused. That's it. Okay, then if pi is a representation. Yeah, sorry, I've managed to get myself this backwards. So, okay, here we go. So if pi is a representation of SO3, okay, and so from our abstract point of view, being a representation of SO3 means that pi taking SO3 to invertible complex matrices of some dimension is a homomorphism. Well, you can get this gives you automatically a representation of SU2 by saying first use phi to map SU2 to SO3, and then use pi to map to GLNC. So it's going to be phi composed with pi, and that takes SU2 to GLNC. Is also a homomorphism. Okay. So on very, very abstract grounds, you've got that maps from that representations of anything. If you have a representation of SO3, then it's going to be a representation of the double cover. Okay, and so to get the representation of the double cover, you basically map down to SO3 and then use the representation of SO3. So the bottom line is this. Okay. So you have a representation of SO3 gives you a representation of SU2. So in other words, anything that you do that you figured out about that SO3 can act on, like SO3 acts on vectors, it acts on planes, it acts on any kind of representation you get, or any kind of gadget that it's acting on linearly, gives you a corresponding representation of SU2. So anything you can do with rotations, you can do with SU2, but not the other direction. But there does not exist a map you know, are a homomorph. Yeah. Anyway, there doesn't exist a map in the other direction, and you can actually see this. The reason that this won't work, one way to see it is actually just pure topology. That if you've got you've got S3, if you know some topology going down to RP3. Okay, so this is your double cover map. There is no continuous map from here. I mean, there's no continuous map from here to here that if you went back here and came back down, it would be the identity. So this just can't exist just for actually topological reasons. It's kind of like, anyway, there's kind of, if you, anyway, you cannot, if you have a really nice map from here to here, but you cannot have a continuous map from here to here. And much less what you really would need, which would be a homomorphism from here to here. So there's kind of a topological argument that you can't do this. But another way to see it, oh, sorry, there's not, sorry. But another way to see this is to see what happens for, and to see more concretely. Recall this picture I tried to draw before. That if you go around a loop down in SO3, what happens is you go around here and you end up, you go from 1 to -1 here in SU2. And so what this says is that, you know, if you try and take your map pi here and lift it, you know, for each, and lift it from, make the map here, whatever pi is here, then you end up with a problem. You end up, you know, when you come back, you're supposed to come back to the same thing, but here you don't know if you've got what, you know, you don't know if you've got the identity or minus the identity. And so the concrete way of saying the problem is that you get, if you try and construct rep and SU2 let me just, let me just say that this would be what I would call a lifting from SO3. You get a representation. You get a sign problem. And then what you see is that your lifted representation is going to satisfy something like this. Okay. So any attempt to take the data you have down here, which is some kind of map pi here, and to kind of locally use this picture to move it up here to get a map on SU2. If you do this, you're always going to have you're not going to know what to do here. Here, do I go to the identity or do I go to the minus the identity? There's always going to be the sign problem. And this is so. One way of dealing with this problem is to say, okay, well, maybe what this is telling me is that I should actually start thinking about representations, but only representations where the homomorphism property is only true up to sign. And these are called projective representations. And so there's a whole theory of, you know, what is a, let's work with homomorphisms only up to sign, and they're called projective representations. And one philosophy is that some people like to have, you'll especially find some physicists fond of it, is to say, well, forget all this business about the double cover group. Let me just stick to SO3, which I know and love. And then whenever I see a spinor representation, I'm just gonna, I'm just gonna realize that it's got this. It's not actually a true representation. It's just a representation of the sign. So this is one philosophy you can pursue about how to do the subject, is to stick to SO3. Don't use the double cover, and then change your representation theory to projective representation theory. But that this then causes a lot of. I mean, a projective representation is a much more confusing object to work with, and keeping track of these signs and how to do this becomes difficult. So I think I and most mathematicians would say, you're better off just learning to work with the double cover, which is it's not like this is something complicated anyway. It's actually in many ways simpler than this anyway. Okay. So that's the spin representation. So that's really kind of all there is to say about this kind of mathematically. So the subtle business about spinor representation is really this relationship between SU2 and SO3, and the relationship between rotations and then these double values, these kind of enhanced rotations, this double cover of the rotation group. The actual spin representation is just something completely trivial. It's the defining representation of the group. It's just the action of 2x2 matrices on C2. Okay, so I wanted to.
I have a question here.
Yeah.
Does this mean that if we identify two elements in SU2, one is positive, one is minus, one is negative, then we get a representation for SO3 to SU2 divided by Z2?
Well, so I would say that SO3 is SU2, with that group. Yeah. So SO3 is, is a quotient of this group by this subgroup. That's true. But I don't know, that doesn't really tell you anything about representations, though. I'm not sure what you.
Oh, okay. Thank you. I see it.
Okay. Yeah. Yeah. So there's several things going on here. There's the topology and the geometry here, but then there's also the fact that these structures are, preserve group laws. Okay, but so let me actually try and do some physics now. So if you've taken a physics class, you may have seen a lot of some of this. You should have seen some of this, but I think I'll spend most of the rest of the time telling you about what do you do with this. So let's actually think about the physics of anyway. So this is something that's going to occur a lot. So is physics of the state space is C2 degree of freedom. So I started with this. I talked about this early on in an earlier chapter to kind of what's the. So remember that the observables. Well, so if you decided, okay, the simplest possible kind of idea of what could be quantum mechanics, not a non-trivial quantum mechanics, is a two-dimensional state space, ignoring the one-dimensional case, and then you've got your observables or self-adjoint operators acting on this, and then the observables are there's only a four-dimensional space, real space of such things. There's the identity operator, and then there's three non-trivial operators. But what I've done here now is that if I take, now I've kind of reinterpreted this problem. So reinterpret with the usual, this thing, which I sometimes call this the qubit, this as thinking of all observables as coming from the spinor representation of SU2. So you can think of this as instead of just kind of abstractly saying, well, I've got a vector space and a bunch of linear operators on it. It's true, we've got a bunch of linear operators here, but it's just the I should actually say that it's from the Lie algebra of Lie SU2. And so these operators are, you can write them in various ways. I want to do this. Let's see. You know, and one way of writing them is these are well, one is okay. So I'm going to ignore the just the identity operator. That corresponds to a U1 action on C2, which is a separate issue. These are, but let's take these to be the XJ. So let's take a basis of the Lie algebra of SU2, which is given by the minus I sigma J. So you just take the sigma, the Pauli matrices, and multiply by minus I, and this gives you something skew adjoint. And these satisfy the nice I don't want to do that. Sorry, over two. I guess I want to do this. Okay, so you can think of this as a story about your operators of the Pauli matrices, or you can think about it. It's these guys. So this is what is kind of natural mathematically. This is what these are the operators you'd actually get from a Lie algebra representation. The representation is unitary, so they're skew adjoint. Or more appropriate for physicists are the ones you would get by multiplying these by an I to make it self-adjoint. And so I'll call these SJ and the physicist version, which are is I. Just multiply this by an I XJ, and then you're going to get sigma J over 2. Okay, so this is really, these are really the same things up to an I, but if you want, from the mathematical point of view, from the point of view of the algebra representations, these are the operators you have. From the physicist's point of view, you would say, well, it may be better to think about these guys, because these guys are going to have real eigenvalues, whereas these will have pure imaginary eigenvalues. Okay, then what I want to, oh, and another thing to say in all of this is that I'm setting h bar is equal to 1. So if you so this is a place crucially where h bar is anyway there's a matter of choosing your convention of what your units are, and I want to choose my unit so that h bar is equal to 1. But if you don't have h bar is not equal to 1, then you're going to have all of these formulas. This formula for this is going to have some kind of have an h bar in it that you have to keep track of. And so you think of here you're going to think of the values of these observables are going to be, the eigenvalues are going to be plus or minus a half. If you throw in the h bar, it's plus or minus a half times h bar. That's the quantization of the eigenvalues of these operators. Okay, so now let me okay, so maybe the first thing to say is is about the relationship to rotations. So one thing that's very, very confusing about spinors is that and I don't know, I want to. Okay, so recall u, well, e to the theta. Let's see. I'll write this down. Yeah. Oh, e to the theta x w vector, where w vector is equal to let's say w1 let's go U2, X2, let's go U3, X3. You know, gives you, you know, of course, this corresponds to rotations by two theta about W vector. And remember that this is when you're doing this calculation involving involving conjugation. It acts on vectors by conjugation. So this is so this is action on vectors. R3. But it acts. But it's just the usual. But just acts on the spin representation, what we call spinors. By psi goes to e to the theta W vector psi. So the thing that's kind of very confusing in terms of language and conceptually, whatever, is you want to ask the question, you know, if I have a spinor representation, you know, it's not just an abstract C2. It comes with this action of SU2, and if you interpret that SU2 as the double cover of the rotation group, then corresponding to a rotation action on a vector, there's a rotation on the spinor, or maybe yeah, maybe it would be better to just say this. Okay, over to. Okay, so there's a confusing, you know, so in some sense you can in some sense rotate spinors, but you have to realize what it means to rotate a spinor is not the same thing. It has nothing, it doesn't actually have anything in particular to do. It's not directly related to what it means to rotate, to do the kinds of rotations you're used to in the real world, where you're rotating R3. Here you're rotating, but you're not rotating R3, you're rotating C2. Okay, so these are all elements of C2. So there's a confusing, so one thing that you can think about is you can think about all of these operators here. These correspond to infinitesimal, these are the operators that generate the rotation action on elements of C2 on the spinors, but they're not really but in some sense by rotation you're not talking about something that's about the rotation action in three-dimensional space. So I think but the fact that these are two different representations of the same. They're not quite two different representations of the same rotation group. They're two different representations of this double cover of the rotation group. So there's a trickiness in language, and if you look at the descriptions of the spinor representation, you often find it very confused about what the relationship is to kind of three-dimensional geometry. And it's because these in some sense are more fundamental objects. You cannot write what spinors in terms of vectors. We'll see later that you can write vectors in terms of spinors, but if you only know what's happening with vectors, you just don't see spinors at all. Spinors are something completely different. But and just as if you just know about SO3 representations, you can't see the spin representation. Okay, so maybe let me just to say quickly a little bit about the physics to end up with this. Okay, so now what?
Professor?
Yeah.
Quick question. So, like, if we interpret, like, how does the rotation acting on spinor, like, does it relate to how, like, the quaternions act on, like, the fourth-dimensional real space? R4?
No, because the whole story is about if you look at, I mean, we're not really using the fourth dimension of the quaternions. I mean, most of us, I mean, when we're using the quaternions, we're identifying R3 with the imaginary ones. And so we're, yeah. So this doesn't, yeah. I mean, in the same sense, you could ask where, yeah. I don't think it doesn't really help. I mean, okay. Here's maybe the way to say it is that those, if you identify the imaginary quaternions with R3, then when you're talking about, you can talk about rotations as things that move around the imaginary quaternions. Okay, but that's really, again, that's the adjoint representation. That's the R3 representation. So the fact that a quaternion can act on other quaternions by multiplication, that's something different. Okay, so you can't, I mean, just yeah, I mean, just identifying quaternions with R3, that doesn't solve your problem. The problem, in some sense, the problem is when you do that, you don't actually see quaternion multiplication. So in some sense, the spinor degree of freedom, it is kind of built into this quaternion multiplication in some sense. And when we put it on 2x2 complex matrices, then it's a C2 degree of freedom. It's a complex degree of freedom, but it really is it's something very new. It's something you just don't see at all. And yeah, I mean, anyway. So it's a confusing thing to talk about. But let me try to say, okay, so one aspect of this confusion is that, so physicists have, so the SJ operators are called spin operators. And maybe we just a bit to get ahead of myself, and we'll maybe we'll start to see this a little bit of this next time. Is that you know, if your representation is on functions on R3, and then whenever you rotate things in R3, you'll get some kind of an infinitesimal rotation of R3 will act on your functions, and that's so you're going to get representations of R3 that way, and those are going to give, you know, those are going to give Algebra representations of SO3. But this is something extra. But the point is, because these things come from the Algebra of SU2, which is a double cover of SO3, these have this significance. So these, in some sense, you often say that these generate rotations on the spinor, on the spinor. So these all of our operators we're interested in, we want to think of as being kind of generators of some kind of symmetry transformations. Well, that's the symmetry transformation, but it's the SU2 one. Okay, so now to give these the physical significance. So if you're given a state, so I'm going to write states like this. And now if I've got one of these operators, this only has, okay, actually maybe let me define it this way. So this is element of H equals C2. Now, what you'd like to do is you'd like to, for each of these SJs, what you'd like to do is you'd like to say that you'd like to associate a kind of physical quantity to it, and to that's something that you can actually measure. And so, what I wanted to say here is that if you get a, so let's just say it this way, so that the 1, 0 is is an eigenvector of S3. So S3, remember, is then going to be a half minus a half with eigenvalue plus a half. Okay, so we say, and so what we say that it has it has three component of the spin we call a plus a half. So this state is going to be an example of a state which has a well-defined value of the observable of the number corresponding to S3, and the name of it is, we say it's the three component of the spin. So we think of it of these guys as being three components of a vector of a spin operator which has three components, and then an example of a state that has a well-defined number associated to it is the eigenvector, which is this guy. So, and the same thing for 0, 1. It's the same thing for this eigenvalue minus a half. Okay. So if you act on with this guy and this guy, this is an eigenvector with eigenvalue a half. Here it's one with eigenvalue of minus a half. And so these are often called the spin up states that have a spin up and spin down. If somebody says your state has a well-defined spin and it's up or down, they mean that it's just it's one of these guys. And an arbitrary state is kind of alpha 1, 0 plus beta 0, 1, where alpha and beta are two complex numbers. And then, as I said, there's a lot. I don't want to go through the details of this again, but this again is that you then say that the measurement theory says the probability of measuring spin up should be the norm squared of alpha divided by alpha squared plus beta squared, and the same thing for this. So the Born's law tells you what if you have an arbitrary one, what's the probability of seeing this or the probability of seeing that. Okay, I'm starting to run out of time, but let me quickly say the main kind of things that I want to say about the physics, and I'll start with this again, say this again next time. And also, actually, those of you who haven't, who've seen some physics, I shouldn't be telling you anything you don't know, just that maybe there's a little bit of different language I'm connecting it to. If you haven't seen the physics, this would probably be a good time to go and look and see if you can find a quantum mechanics book and see what the quantum mechanics book tells you about the physics of a spin 1/2 degree of freedom. This is what's called spin 1/2 degree of freedom, and especially, and for instance, what happens if you put it in a magnetic field. So let me tell you quickly how that works. Well, you can think of how do I want to do this? Okay, so to give a physical interpretation to some kind of arbitrary linear combination of these observables, of these spin observables, it turns out that if you take a spin 1/2 particle, and so this involves physics that we're not discussing now, but it's kind of the bottom line of some more complicated story about how particles interact with electromagnetic fields. But the physics of electromagnetic fields, so some physics that we're not getting into at all. Implies that if you have one of these spin 1/2 particles and you put it in and you assume that it's very heavy, so it's actually not going to move around, but you just have it sitting there and you apply a magnetic field as a magnetic. Then you get so in a magnetic field B vector, you have your Hamiltonian is H is equal to, and then there's a bunch of standard constants in this, I don't know, GE over 2MC S vector dot B vector. Okay. And now what this means is that this means S1 times B1 plus S2 and B2, S3 and B. Sorry. Okay. So these are 2 by 2 matrices. Remember, these are, so this is a linear combination of 2 by 2 matrices. These are just some various physical constants, including the mass, the speed of light, and anyway, these things that occur. But all this really is this is really saying that if you've got a spin 1.5 particle, you put it in a magnetic field, and it's heavy enough so you don't have to worry about its motion. But what it's going to do, it's going to be described by this state in C2, and then the state will satisfies I dd, the Schrodinger equation. And the solution is as a function of time, you're going to get e to the minus I t h. Okay. So you always get this. Okay. Okay, so now what this let's see what's happening. Okay, so what's so this is kind of this basic fact about how you what the dynamics of quantum theory is. Sorry, this is 0. That the Schrodinger equation always tells you if you can exponentiate the Hamiltonian operator, then you get the time dependence of the state just this way. And here, the Hamiltonian operator is just this this 2 by 2 matrix. So you pick a background magnetic field, a constant magnetic field. You get a certain 2 by 2 matrix, and how the thing is going to behave then depends on just as given by this formula. And everything that we've done last time and a little bit earlier was kind of all it tells you exactly what's going to happen. What's going to happen when what do these exponentials look like? In particular, these exponentials are exactly the kind of thing that you get if you're doing a rotation. And so if you look at what this guy is, you find that he's actually the what is he? He's the rotation. Let's see. So he's going to be. So this is rotation. Is it rotation in this funny sense about over B by angle, and what is the angle? Comes out to GED over 2MC T. So if you want to kind of understand, you can understand what a state is going to do if you put it in a background magnetic field, a state in a fixed place, is it's going to move. Its phase is just going to change by at this constant rate if the magnetic field is constant. And if the magnetic field is not constant, if B depends on a function of time, then you're going to get a much more a trickier equation to solve, but you can do it, and that gives you a lot of the complicated physics about what happens if you take just a spin 1/2 particle and put it and start applying magnetic field to it and start varying the magnetic field in various ways. Then you're just going to get more complicated equations here where this depends upon time, and you're going to have to but you're going to have straightforward solutions to those. And these are the sort of thing it tells you about what happens, for instance, in NMR machine, in a nuclear magnetic resonance machine. When you do an MRI, what you're doing is they're basically hitting the nuclei in your body of time varying magnetic fields and seeing what happens according to this equation, and then using that to kind of image where to image what's going on. So maybe I'll start again with this at next time. I want to say maybe a little bit more about the physics, but again, the advice for I'm hoping that people who've had some physics background will just will now see how what I've been doing connects up to what they've seen in the physics, and that if you don't have some physics background, you might want to start looking for a physics book to read more about the physics of this. There's a lot of intricate, complicated story here, and I can't say more than a little bit of it in this class because getting into the physics starts to become a whole different subject. Let me stop here then. Are there any questions about any of this? No.
Really quickly, Professor. So I feel like we're using the word spinor a lot, and it seems to me that they have different meanings, but I want to verify that.
Okay.
That we have the spinor group and then the spinor representation, and then you're describing the vector as a spinor.
Right.
Am I those terms correctly, and are those different?
Okay, so to get the standard terminology is to say the spin, not spinor, but the spin group. So whenever this double cover of the rotation group is called the spin group, and then and then what you always get is for every spin group, it has a specific representation, like this one, the spinor representation. And in this case, in 3 dimensions, it's just the defining representation. So it's the representation. But you're right. The other language I should have told you about, which I'm using a lot, is to say that an element of the spinor representation vector space, I'll call a spinor. Okay, so the spinor representation is on a C2, and elements of that C2 are also called spinors. Does that help? Okay.
Yes.
Okay. Okay. And so, any other questions? And again, I'll stick around later. So if people want to stop by after the class and connect to the other Zoom thing, that would be good. I should maybe a little bit more just to say about this. There are some later parts of this chapter 3, these things about the Heisenberg picture and complex projective space and the Bloch sphere. I may start off by saying a little bit next time. To be honest, those things are there actually mainly because much later on in the course, there was something where I wanted to use those, and I thought it would be better, they could be defined earlier, so I would do it earlier. But these are, I'll say a bit about these things, but it might be better to kind of hold off going into any detail in them until later in the class when they're actually going to get used. So if you're reading along in this, try to what you should have seen for what I'm talking about. It goes through the section 7.1 and 7.2, and from the rest of the chapter 7.3 on is stuff which you don't need to worry about now, or next time I may say something about 7.3, but it's the stuff about complex projective space with Bloch sphere. I think you may find interesting, and it'll appear later. But maybe better to hold off on it until later, till we're actually going to use it. And what I really want to get to next time is the stuff which is in the next chapter, which kind of answers kind of completely the kind of obvious question here is like, not just, here I've shown you a very specific representation of SU2, but there's the question, and we saw all of the representations of U1. Well, what are all of the representations of SU2? Well, now we've gotten to the point that we can actually start to approach that problem and to write down all the representations of SU2, write down all the representations of SO3. And that's the main thing I want to get started on next time. Okay, so if you want to read ahead on that. And that's something which, even if you don't had even if you've had a fairly good physics course, I think there'll be a bunch of stuff there which you haven't seen, so you might want to start looking at for next time. Okay, any questions? Okay, so I'll close this off, and then to see any of you who want to stop by, come back in a minute. Bye now.
Thank you. Bye.
Thank you.
Thank you.
All right.